Everybody, good afternoon. So today we have the first general seminar of the year. So Happy New Year to everybody. We are just in time. And we are pleased to welcome Matteo Gatti, who comes from Polytechnique, and who will talk to us about coupling of excitations and coupling of spectroscopies. And the floor is yours.
Thank you very much, Emmanuel, for the kind invitation, and to all the organizers for the organization of this general seminar of the lab. It's always a pleasure for me to come to the LPS because I always find a very good atmosphere for discussions. And please keep it alive. It's very important also for the people outside the lab. So thank you very much, and thank you very much to each of you for coming out in the cold and to come to the seminar, and also to those that are online. I hope that each of you will find something useful and interesting in what I'm about to say. It's true, I don't come from very far. I'm actually working at the École Polytechnique and at the Synchrotron au Soleil. So the LPS is the middle point between the two. So it's a pleasure to be here. So I would like to start by thanking the other people of the theoretical spectroscopy group at the École Polytechnique. I have the luck and the pleasure to work with every day. In particular, Lucia Reining, Francesco Sottili, you may know, but also all the non-permanent people of the group. It's at the moment a very international group, and it's a real pleasure to work with all of them. So what are we interested in? Which are the typical problems we are interested in our group? I can give you some examples. And the first example is the fact that we are interested in finding, for example, new materials for photovoltaics. So we are interested in the problem of new materials for photovoltaics. But our point of view is a fundamental one. I'm not able myself to build a solar cell. So it's important that we team up with the experts of photovoltaics and we give our contribution. And in particular, we have started a PhD project. It's the PhD project of Jean that is about a very fundamental question: how to calculate in a very accurate way the band offsets of interfaces. It's an old problem that is still open, and we like to give our contribution in this kind of problems. And then our aim is to be useful for people working in photovoltaics, in particular here on the plateau, the people from IPVF we are in contact with. This is not the only scientific question we are interested in. On the other side, we are not only interested in new materials, we are also interested in old materials, in ancient materials of cultural heritage. And this is a question that we have addressed some time ago in collaboration with the people from the Museum of Natural History in Paris. And the question is, which is the origin of the colors of this first color photography of the history that dates back of more than 100 years. And here you see the specimen. It's a solar spectrum. It's not very clear, but you can excuse the fact that this dates back to a very long time ago. And again, we are not the experts of cultural heritage. This question doesn't come from us. It comes from the experimental colleagues working at the museum. And our role was, again, fundamental, how to try to help to understand the origin of the colors of this photography. Now, I will not talk about this, but if you are interested in this last subject, you can ask your colleagues in the room and in the lab, because this was a large collaboration with other people, other spectroscopists. And in particular, you can ask Matteo and Odile, because they would team up as well with the people from the museum, Victor and Marie-Angélique from the museum. So if you want to have the answer to this question that I will not address in the following, you can have a look at this paper. And if you are curious about our contribution, you can have a look at this video on YouTube. So I will not talk about this in the following, but for us, the interesting question is what these two kinds of problems have in common. In principle, they seem very different. They are diverse questions. In one case, we are interested in new materials. In the other case, we are interested in old materials. What do these two problems have in common? And the first answer is actually Edmond Becquerel, because Edmond Becquerel is the inventor of the first color photography of the history, and at the same time is the discoverer of the photovoltaic effect. So the first link between these two problems is Edmond Becquerel itself. And then in both cases, we are interested in the interaction between light and matter, the sun and the matter in the case of photovoltaics, but also in the case of the first color photography. And there is also a question related to the charge transfer at interfaces between different materials. So different problems can have fundamentally same things same problems that we have to solve at the fundamental level. And indeed, behind the scenes, there is always the same problem. It's a many-body problem that we all know from quantum mechanics. We have a Schrödinger equation to solve. And by the way, I'm a theoretician, so I work with mathematics a lot. So this is the language that we use every day. And this is in principle what we are supposed to solve. It's a many-body Schrödinger equation for a large number of electrons, very large. And we all know that from quantum mechanics, if you are interested in observables, we are able to calculate them as expectation values of some particular operators. So all this is very well known. The problem is that it's very often not the right way to go, because this has no solution for the kind of problems we are interested in, large number of particles and interaction, excited states, so interaction between light and matter. Nowadays, we can calculate these integrals using stochastic methods like quantum Monte Carlo, but typically these methods are used for ground state properties, total energies, not for excited states at the moment. There is still some work to do. So we have to look for alternatives. And the alternatives is basically we try to rewrite quantum mechanics. So instead of calculating observables as expectation values of operators with respect to the many-body wave function, in the language of mathematics, this is a functional of the many-body wave function. We don't go along this way. We actually try to find different functionals, these different expressions for the same observables in terms of other quantities. And these other quantities that I call Q we can have different choices. If Q is the electronic density, this is very well known. It's density functional theory, but it's not the unique choice. We can use density matrix. We can use a Green's function, and the Green's function expresses the idea of propagation of additional particles in the system. All these are possible choices, but they have in common one aspect. The problem is that very often we don't know the functional dependence for the observable interest with respect to the key quantity. And the other problem is that we are very often not able to calculate the quantity, the key quantity. So the choice, the common strategy is that we trade an equation that we know very well, but we are not able to solve, with an equation that we don't know, that we have to approximate, but then we are able to solve. This is the common strategy that is in common for all these different ways of replacing the quantum many-body problem with functional theories. And the important advantage that we have here is that this object, the many-body wave function, is growing exponentially with the number of particles, while these other quantities that we call reduced quantities have instead always the same number of degrees of freedom independently of the number of particles. In the following, I'm not going to discuss about all these active field of research because it's quite technical. I will use the language of Green's function theory of propagators, where we introduce new key concepts like effective particles, effective interactions, coupling between particles. So this is the language that I will use, but behind the scenes, there will be always equations in terms of these objects. So this is the outline of the talk. At the beginning, I will try to convince you that very often we can understand the effect of the electronic interaction in terms which very often we call electronic correlation, in terms of coupling of excitations. And this idea that we can understand correlation as a coupling of excitations suggests also a practical strategy. That is the fact that we can combine the different spectroscopies that are measuring independently the different excitations. And I think this is an important remark, especially in these times where each of us is actually pushed towards more and more competition. We know that there is a push for more competition between individuals, between groups, nowadays between even labs. What I would like to show instead is that it's very important to recognize that each of us is complementary. We cannot solve the entire problem from deriving new functionals until building new solar cells if we work all alone. It's important to combine the different expertise. And by experience, I can also say it's a lot of fun because you put together different people with different expertise and you can learn a lot. And with this, in the following, I will give you some examples, some practical examples, if I have time. And for this, I would like to thank, first of all, the companions of this adventure that are responsible for the results that, if I have time, I will talk about. And I would summarize them saying that it's the L-Cube team, because it's Alessandro, Alberto, and Alex, who in different roles contributed to this collective enterprise to understand effects of correlations in different domains and in the combination of different spectroscopies. On the other side, I also would like to stress the fact that I will, after the introduction, I will spend a lot of time in discussing collective excitations such as plasmon and excitons. I know that the audience is quite mixed here, so I have selected topics that have an important pedagogical content, but along the way, we will also find surprises in classical topics like the homogeneous electron gas. So I hope that each of us here in the room can find something interesting, the newcomers, some general introduction in the field, and those of you that are even more experts than I am, some news that can be exciting also for you. So I don't mind if I don't finish all this. Please, let's keep this discussion informal. So if you have questions, if you have comments, remarks, please stop me, okay? If I don't finish, there will be another occasion for those of you that are interested to continue the discussion. And as I said, it's always my pleasure. Okay? Okay, then let's start. So the first idea that I would like to discuss is the fact that we can understand electronic correlation in terms of coupling of different excitations. So the many body, this is the representation of the many body problem. We have a material with many electrons that are here represented by these red spheres. And the question, the simplest question we can ask is the following. How can we know the properties of one electron? We know that electrons are fermions, and fermions have the property that we cannot distinguish them. So if we want to know the property of one electron out of n electrons in the system, how can we do? That's a question, which can it can seem trivial from the fundamental point of view, but practically it's not, because in principle we have to deal with the many body wave function. But in practice, how can we do? How can we know the properties of one electron? And the experts in the room have already the answer. One possible answer is to use photoemission spectroscopy, where there is an incoming photon that is used to emit one electron from the system. And then you can think that this electron is out of the system, is detached from the system, and you can distinguish this electron from the others. Then what you are left with in the electronic system is the fact that you have a hole, and this hole is represented here by this white sphere, and this hole is a positive charge, and the positive charge is actually a charge excitation in the system. Is there a question?
No, it's
okay.
It's not the same.
So we are left in this photoemission process with a hole in the system, positive charge, a charge excitation. Now the question is, what happens? We have created a charge excitation in the system. The question is, what happens? Now let's make the hypothesis that the particles, the electrons, are non-interacting. So what happens? According to you, what happens? Any idea? At least for the non-experts? Nothing happens. Okay? If the electrons are non-interacting, they are not feeling the fact that there is a new different particle in the system, a charged particle, because there is no Coulomb interaction. So the other electrons don't care about the fact that there is a positive charge in the system. Okay? So this is quite boring. Luckily, there is interaction, and luckily there is interaction that is paying our salary, right? Without Coulomb interaction, we will be unemployed or we will be doing something else. Luckily, there is interaction. This is boring because if we look at the probability of the electronic excitation of a given energy, which is called the spectral function, and it's represented here, and mathematically it's the imaginary part of the Green's function, we just have a sharp peak, which means that 100% of the probability is represented by this sharp peak to remove one electron from the system at the energy that this electron was occupying in this energy level scheme. Again, something that we can intuitively understand, but pretty boring. Now, let's see what happens if the particles are instead interacting. Well, the electrons will feel the presence of a positive charge. They have a negative charge, so they will feel that there is another charge that is positive, and they will react for the presence of this particle. So in general, the electrons will change their position. And in terms of the language of many body perturbation theory or Green's functions, it means that they create electronal pairs, meaning that they move and they have a hole that is the position that they have left behind. So we can represent this reaction of the electrons that are moving for the presence of this positive charge in terms of creation of electronal pairs. And we call this polarization screening of the additional charge in the system. Now, just to make this discussion simple, I will just talk about electronal pairs. So the excitation of the charge of the electrons. I will neglect the spin degrees of freedom of other degrees of freedom like lattice in the system, just to keep all this simple. And it's just an example of what can happen in the material. Many other things can happen. Here it's just an example. So what happens is this creation of additional electronal pairs in the system. And we can have in the following also, we will discuss about the creation of collective excitations that are, for example, plasmons and excitons that I will introduce in a moment. All of them are neutral excitations. We don't change the charge in this case. And in general, we can understand the interaction between this photo hole that has been created by the photon that has removed one electron and all the other electronal pairs in terms of coupling between the charge excitation and these different kinds of neutral excitations. So this effect is related to the interaction. Without Coulomb interaction, there would be no coupling and there would be no pairing of these different kind of charge excitation and neutral excitations. That's why we can understand the effect of electronic correlation in terms of coupling between different kind of excitations. In the language of Green's function theory, we introduce effective particles, effective interactions. And this is the first effective particle that we introduce. It's called quasi-particle. And we can understand a quasi-particle as a sum of a particle, an electron or a hole, and the polarization cloud around the particle that is given by this ensemble of electronal pairs that is acting to react for this excitation that is due to the presence of this positive charge in the system. How this is expressed in terms of the spectral function. So instead of having this sharp peak at the energy of this single particle level, in these cases, we still have a prominent peak that is associated to this quasi-particle that is behaving like a renormalized single particle. So it's not very different from the non-interacting case, but the peak has now a finite width, and this corresponds to the lifetime of the excitation. It doesn't last forever, so something is happening in the system. But we also have other excitation, other peaks in the spectral function that are called satellites. And these effects, this broadening of the quasi-particle is related to the satellite, to the lifetime, and this presence of additional structures in this spectral function are all fingerprints of electronic correlation. So by studying, for example, satellites, we can understand more about the coupling between quasi-particles and neutral excitation in the system. So we can study the electron-boson coupling. All these neutral excitations can be understood as bosons in terms of a spectral function that can be related to a photoemission spectrum. So this is the idea that we can combine different spectroscopies, for example, photoemission and the spectroscopies that are measuring this screening in order to understand the effect of correlation. So I think that in the following, it's important to discuss a bit more in detail about this screening effect, this polarization effect, this reaction effect, if we want to understand more about this coupling. So in the following, I will discuss more in detail about the properties of these neutral excitations that are coupled to the hole that is created in the system. And I will introduce two typical collective excitations that are plasmons and excitons. And mathematically, the screening is related to the inverse dielectric function. And the inverse dielectric function can be related to the density response function. And V is the Coulomb interaction. So without Coulomb interaction, there is no screening because epsilon minus 1 is just 1. So no screening. So the important ingredients are the Coulomb interaction and the density response function. And the theoreticians calculate these quantities. And importantly, experimentalists measure these quantities as well. In particular, by using inelastic scattering of photons or electrons, you can directly access the loss function, that is the minus imaginary part of epsilon minus 1 of the inverse dielectric function. And as a function of momentum transfer and excitation energy. Now, the scattering of electrons, you all know here, it's called electron energy loss spectroscopy. Typically, it's done in a transmission configuration, so the electrons go through the sample. In the case of X-rays, of scattering of photons, this is called non-resonant inelastic X-ray scattering if the photons have high energy as the electrons that are used in the microscope to do EELs. If I have time, I will go back to the case where the photons have energies that are comparable to the edges of the absorption edges in the materials. This is called resonant elastic X-ray scattering spectroscopy. Now, the point is that in principle, both techniques, EELs and non-resonant elastic X-ray scattering, measure the same quantity. But in practice, from the experimental point of view, they are very complementary. The momentum range and very often also the energy range that two techniques can measure are complementary. So it's also in this case, it's useful to combine the two because they can give complementary information. From the theoretical point of view, we always calculate this quantity here that we can directly compare with the experiment. So this screening is something that we can calculate, we can measure, and it's important information to understand some correlation effects in materials. Now, let's talk about plasmons that are typical collective excitations that form this screening in materials. So let's imagine that we have an atom that is just represented here by a filled level with one electron and one empty level. And let's imagine that this atom gets excited. So one electron is promoted from occupied to empty states. And what happens is the fact that this excitation can be understood in a first approximation as a dipole. It's an electron-hole pair, and it's like a dipole that we have all learned in classical electromagnetism. Now, if we have, instead of one atom, a collection of different atoms, we have all these different dipoles. They are like antennas. And we can think that the different antennas can resonate together and they form a different signal. And this is indeed what happens if we take into account the effect of the Coulomb interaction, that is coupling the different dipoles in the material. And this effect of coupling all these different dipoles and make them resonate together is what gives rise to plasmons that are collective excitations of the electronic charge in the material. And they are probably the simplest example of emergence, a result that is due to the interaction between the ingredients in the material. It is always reminding us that the whole is different from the sum of the different parts. This is also reminding us that we have to shift our attention from the elementary constituents of the material to the interaction between them. It's always very important in our domain to take into account the interaction between all the different constituents. So the result of all these interactions is the creation of a new excitation that is called plasmon. It is a collective excitation. We can represent this pictorially as in the electron liquid as different oscillations like what you have on a surface of, I don't know, a sea surface when you throw a stone in the sea. So this can be a representation of plasmons. And for the Italians in the room, this is something very natural because all Italian kids are fed with plasmon biscuits since they are born. Okay, so in Italy, there is a brand of biscuits that is called plasmons. So this is something you can also explain to Italian kids that plasmons are useful. From the mathematical point of view, what we are just describing is the fact that on top to Hamiltonian that is describing non-interacting electrons, we have to take into account the Coulomb interaction that is making these antennas resonate together. And this, in the language of Green's function theory, is called random phase approximation. We take into account the long-range part of the Coulomb interaction that is responsible for the creation of these plasmon excitations. Now, the first example where plasmons were studied is the homogeneous electron gas that I guess most of you in the room are familiar with. Is just a model where instead of having the crystal potential that is due to the presence of the atoms, you just take a constant potential. So the electronic density in the ground state is just constant. The Fermi surface that is dividing occupied to empty state is just a sphere, the surface of a sphere. And then we can have, so it's a simple system, but where there is electronic interaction. And we can have a look at the different kinds of electronic excitation in the response function or in the inverse electric function. And they come in two kinds of interactions. First of all, we have the simple electron-hole excitations, where we promote one electron from the occupied states to the empty states. This comes with the wave vector that I call Q and a given energy. And if we represent all the possible electron-hole excitations in this map, we get this, what is called the particle-hole continuum, as a function of excitation energy and wave vector. And it's all this part here. It's called particle-hole continuum because there is an infinite amount of different possibilities of exciting electron-hole pairs. Okay? So on top of this, there is also another excitation, and this other excitation is this collective excitation that is a different kind with respect to this electron-hole excitation, and this is the plasmon. And in the homogeneous electron gas, in the random phase approximation, we have this high energy excitation that starts at this energy omega p, that is large energy, and then it has a parabolic dispersion until it merges into this particle-hole continuum, and then we cannot distinguish this collective excitation with respect to the other particle-hole excitations. Now, this is a model. The question is whether these excitations exist in materials. And again, the experts already know the answer. Yes, they exist. Here, I give you a very simple example. It's a measurement of the non-resonant elastic X-ray scattering of bulk sodium. That is the simplest material we can think of that is closest as possible to the homogeneous electron gas. And indeed, if we make a cut in this kind of plots at a given momentum and we plot the spectrum as a function of excitation energy, we get a peak. And this peak corresponds to the plasmon excitation that we can measure and we can calculate in different ways. It's not important here, it's just an example. And then we can do experiments as a function and calculations as a function of wave vector, and we can calculate and measure the dispersion of this collective mode. And we see, as expected, that by increasing the momentum transfer, the peak energy moves to the right, so to high energies. And this is something that is in line with the expectation from a diminished electron gas. But first surprise, if we look carefully here at large momentum transfer, at large energy, we see that there is a shoulder, and the shoulder here has an energy that is more clear in this blow up, that is more or less 12 electron volt. And now if we do simple math, this 12 electron volt corresponds to the double of 6 electron volt that was the energy of the plasmon at 6 electron volt. It means that since we are still in the linear regime, with one photon, we have been able to excite twice the plasmon. Plasmon is a boson, so we can excite a boson once, twice, 3 times, and so on. And the energy we expect to have this excitation is double and the triple of the energy of the excitation of the single boson. And indeed, this is the case. Now, this is something that you can measure in non-resonant elastic scattering. It's more difficult in the case of EELs for technical reasons we can discuss about. But it's a challenge from the theoretical point of view. If we just use this simple random phase approximation, we cannot get this. And this is already a first surprise because we have to go beyond this random phase approximation, even in this very simple material that is sodium. So there is some work to do from the theoretical point of view. And if you are interested in this problem, we have done some work along this line in this article here. So even in sodium, there are interesting features. Now let's go back to this description where we have said that there is an atom that is excited because one electron is promoted from an occupied to an empty state. There is something that we have forgotten. It's the fact that even this electron-hole pair is composed by one positive charge and one negative charge. So there is some interaction even between the electron and the hole here. And this is something that we have not considered so far. And then we have to take into account this interaction between the electron and the hole. And in particular, if we are then in a standard system, we have also to take into account the fact that there are all the other interacting electron pairs that are providing a dielectric background. And instead of having the Coulomb interaction between the electron and the hole, we have to take into account another kind of interaction that is screened by all the other electrons in the system. And this is indeed baptized here with a different name. I call it W instead of V. And W is this screened Coulomb interaction that is screened by the inverse electric function, and it's screening the bare Coulomb interaction that I call V. And this is an essential ingredient to describe excitonic effects. This interacting electron-hole pair is called exciton, and the interaction between the electron and the hole is attractive. So instead of having a plus sign, I put a negative sign to indicate that there is an attraction. And this attraction is mediated by this screened Coulomb interaction. So the total Hamiltonian here has 3 terms. If I stop here, this is the random phase approximation. If I include also the electron attraction, I can describe besides plasmons, also excitons. And this is something that you can derive from Feynman diagrams. Also, instead of using this end waving derivation that I've just discussed. If you are interested, you can, for example, take a book on Green's function theory, and then you will find that the description of this correlated electron-hole pair is related to a two-particle Green's function and the solution of an equation that is called Bethe-Salpeter equation that is providing this description. All this can be understood in terms of these different terms and this different electron-hole interaction, a repulsive term that is creating in the long range plasmons, and an attractive term that is screen, and it's creating excitons in materials. Now, this seems to be very complicated, but actually it's very similar to the hydrogen atom problem that we all study when we study quantum mechanics, with just the modification of the fact that we have to take into account the screening. So instead of having the bare Coulomb interaction, we replace it with this screen Coulomb interaction. But the result of this, in the simplest approximation, is just the Vanier model for excitons, where the screen Coulomb interaction, instead of having this bare interaction that depends on the distance between the position of the electron and the hole, is renormalized by this dielectric constant. And the result of this is the Rydberg series of discrete states that are the excitonic states. Now, this is the simplest possible description of excitons, but it has a big advantage that we can understand some important element of physics, which is the fact that normally materials that have large gap have smaller dielectric constants, which means that there is a larger screen Coulomb interaction and therefore larger excitonic effects. And if you're interested, we can discuss a bit more these qualitative trends. I would like also to spend a remark on the fact that 2D materials are becoming fancy nowadays, because the screening in low dimensions is not described by this macroscopic dielectric function, just a number. It's differently, qualitatively different. And the important thing is that in general, in low dimensions, the screening is inefficient, meaning that the screen Coulomb interaction is large and excitonic effects are important. Now, here I will not talk about 2D materials, but I will take the material that probably has the largest gap in the world, which is solid helium. The helium atom is the atom that has the largest ionization energy. And here, in this case, we have calculated the loss function here of solid helium at high pressure, where this material is a simple HCP crystal. And we have done two different calculations, one calculation without electron-hole interactions, and a calculation taking into account electron-hole interactions. The calculation without electron-hole interactions is this black spectrum, and the onset of this black spectrum corresponds to the band gap of the material. And you see that in this case, the band gap is more than 25 electron volt. So very large band gap, which means it's an extreme insulator. And we expect that in this case, the screen Coulomb interaction is very large because the screening is small. And indeed, if you compare the calculation with and without excitonic effects, you see that the difference is very large. This is the big advantage of theory. You can switch on and switch off the interactions to see their effects, which is something that you cannot do in experiments, at least not so easily. So here there is a sharp peak that is inside the band gap of the material, and this is characteristic fingerprint of an exciton in a material. And the binding energy, which is the energy to break this electron-hole pair, is very large, is of the order of, I would say, at least 5 electron volt in this case. So very large. So excitonic effects are very strong here. And that's why it's, for us, interesting to study this material. Now, this was the loss function calculated in the dipole limit, meaning for wave vector going to 0. Now I'm showing you the spectrum calculated at the wave vector that corresponds to a Bragg reflection, in particular the 002 Bragg reflection in the HCP unit. So I've just changed the momentum in this representation here, and you see that the spectrum is very different from the previous one. Now, in this case, I have just added a small component of the order of 10 to the minus 6 with the spectrum in this direction along 002. So I'm actually showing a wave vector that is 002 plus 10 to the minus 6. Why I'm doing so? Because now I change the component. I take an in-plane component, again of the same order of magnitude, 10 to the minus 6 in the in-plane. So the wave vector is changing by nothing, 10 to the minus 6. And you see that the spectrum is completely different. It's the green curve. Before, I had this orange curve. So you see that by changing slightly the wave vector around Bragg reflections, the spectrum is completely changed. You can switch on or switch off the main exciton peak in the material by slightly changing the momentum transfer, the wave vector around the Bragg reflection. Now, this, you can argue whether this can be measured, whether this is real. And the first answer is that actually for exciton, this has never been measured. Okay, it has never been calculated, so it's first time. But for plasmons, this has been already demonstrated to be true. So this is not a complete craziness of theoreticians. In the case of graphite, and if you are interested in this, you can have a look at this work. Now, the question is where this is coming from, this very strong anisotropy at Bragg reflections. And again, we take advantage of the fact that we are theoreticians and we can suppress or we can include interactions. Now, if I suppress this term in my Hamiltonian, that is this Coulomb interaction, V, that is repulsive, and I calculate the spectrum, I have for the two different wave vectors the same spectrum. So the anisotropy is there just due to the fact that there is this Coulomb interaction. If I remove this Coulomb interaction, the anisotropy is not there. And this can be understood in the language of this this domain. It's called an effect that is related to crystal local fields, and it is related to the fact that helium, in contrast to the homogeneous electron gas, is a very inhomogeneous material. And we have to take into account the inhomogeneities in the polarization in order to explain this effect. These inhomogeneities in the polarizations are related to the fact that when you apply an external field to the material, this material will react again and will try to counteract the external perturbation by the creation of microscopic fields. And these microscopic fields are important for systems that are inhomogeneous. So this would not be visible in the homogeneous electron gas. Now, in helium, inside helium, we can play with pressure. Helium is a material that is highly compressible, and we can simply play with pressure in the computer or in the experiment. And we can ask ourselves, what happens if we change pressure? And the answer is that the effect increases if the density or the pressure increases. So we can think that if we increase the pressure, the crystal is more homogeneous. The atoms are getting closer and closer. So we would expect that if we increase the pressure, the system is more homogeneous thanks to the homogeneous electron gas. So the effect of this anisotropy should reduce. But here we are finding something different. We are finding actually the opposite. The effect is increasing with pressure. How can we explain this? Is the fact that the system, the helium, not only is becoming more homogeneous, but it's also becoming more polarizable. Indeed, if you just look at the intensity of the peaks here to make the discussion simple, you see that the intensity of the peaks increases with pressure, which means that the system wants to react more and more if we increase the pressure. So we expect, this is a prediction, that if you want to measure this as a function of pressure, this effect should increase in helium. Now, I'm showing helium because it's the simplest case where we can understand this effect, but this effect is absolutely general. It has nothing to do with helium. It has only with helium, but it has something to do with these interactions. So helium may be under pressure, may be difficult from the experimental point of view, but if you have another material that has a sharp peak, a sharp excitonic peak, and it's inhomogeneous and it can be polarized, we expect to find the same anisotropy. And this is a call for experimentalists in the room that want to take up the challenge. Second challenge for the experimentalist, and here I will just flash this aspect. I would like to advocate the fact that studying the exciton band structure, so the exciton energy as a function of wave vector, is very important if we want to know the exciton character in the material. I don't have time to enter into the details of this, but again, I would like to say that it's important to be able to do experiments as a function of pressure. I will also skip this. It's just to say that the motivation of studying helium in this case was coming from experimentalists. And in particular, it's the group in Poitiers that are studying helium bubbles in semiconductors. And also this is not something completely new in the lab, because there has been a PhD thesis some times ago by Dario Taverna about helium bubbles in semiconductors and in materials in general. And the question that experimentalists came up with is the fact that if you compare different spectroscopies, you find different trends of the spectra as a function of pressure. So we work together to answer this question. But here I wanted just to use helium as an illustration of what are excitonic effects. So what we have seen so far is the fact that if you have a material with a large gap, you expect to find excitonic effects that are strong. Now we take the opposite limit of a metal, like the homogeneous electron gas. And in a metal, the screening is qualitatively different with respect to a semiconductor. And indeed, the screen-Coulomb interaction, the macroscopic screening of the screen-Coulomb interaction, give rise to an interaction that has a mathematical form that is different from the case of a semiconductor. And indeed, we say that in metals, the macroscopic screening is perfect, because if you look at the static screening in the long wavelength limit, epsilon is infinite, which means that the screen-Coulomb interaction should be killed, and we don't expect to see excitonic effects in metals. So this is the general expectations, and this is for a normal case of valence electrons. For core levels, the story is different. If you are interested, you can have a look at the classical works of different people that are cited here in the slide. So the question that we have now is, are really excitonic effects zero in metals for valence excitations? And we go back to the simple case of the homogeneous electron gas. In the homogeneous electron gas, we have already discussed the fact that the main collective excitation is this plasmon that I'm now showing again for a density that corresponds to the density of bulk sodium. And here I'm comparing again a calculation without excitonic effects in green. It's what I call the random phase approximation, and the calculation with excitonic effects, I called Bethe-Salpeter equation. And you see that the difference is not so important. The two are very similar. If we look at the static screening, which means if we plot the inverse electric function at frequency 0 as a function of wave vector, and we compare the calculation done in the random phase approximation with an accurate calculation that we can do using quantum Monte Carlo, there are differences, but qualitatively, it's the same behavior. At Q equal 0, epsilon minus 1 goes to 0 because epsilon goes to infinity. And for large momentum transfer, there is no screening, and epsilon goes to 1. Which means, by the way, that the screening is perfect only for Q equal to 0. Which means that in the short range, even in random phase approximation, even in the metal, the screening can be far from perfect. Now, in the homogeneous electron gas, we can play with the parameter of the density of the homogeneous electron gas. So we go to a regime that is the regime of simple metals like sodium to a regime of low density. And in this case, the situation completely changes, and completely changes from the qualitative point of view. If you look at the static screening, you see that screening in this accurate calculation changes sign. It becomes negative. In the random phase approximation, it's always the same. But if you take into account effects that are beyond the random phase approximation, the screening is changing sign. It becomes negative. And then if we look at the dispersion of the collective modes in this material, in this regime of low density, we see that the plasmon has now a negative dispersion if we take into account excitonic effects beyond the random phase approximation, which doesn't change. And moreover, there is a new mode that is strongly dispersing, and it's dispersing with the negative slope. And this, we can understand all these two effects, the fact that the slope of the plasmon changes sign, becoming negative, and the fact that there is an additional mode, we can understand them as having an excitonic origin, because the difference between the green curve and the red curve is just the fact that we take into account electron-hole interaction. if you are interested in this, there is a paper that should come out pretty soon in physical review letters about this. This is just a very short summary to say that actually, in this case, we discover that there are excitons in metals, contrary to what we expect. And it's also to show that there are surprises also in models that have been studied for so long time, like the homogeneous electron gas. Then we can also analyze this excitonic mode, this collective mode, because we can represent the wave function of the electron pairs that are giving rise to these collective modes. And okay, I don't want to enter into the details of all this. I just compare the case of the uncorrelated electron pair and the case where we take into account the electron attraction. In the case of the uncorrelated electron pair, this wave function would have the same density anywhere in the material, would be just a constant, because again, the electron and the hole doesn't feel any interaction. So this would be the boring side of our life. Instead, if we take into account the electron attraction, the typical effects that we see in materials is a localization of the electron charge around the hole that I fixed at a given position here in the middle of the figure. So this is the representation, the two-particle representation of this excitonic mode that we have discovered. And this localization is normally explained in terms of the fact that there is electron attraction. Now, I also represent here the plasmon excitation. Now, the plasmon excitation can be here analyzed because the plasmon in the gas is an isolated pole, and we can really directly look at the wave function of this collective mode. And this is what we obtain. And what is interesting to here to underline is the fact that this is not something that is completely delocalized. We have always in mind the fact that plasmons are delocalized excitations because they come from this Coulomb repulsion. We have in mind this picture of these waves, but actually this picture is very different from the previous one. And also in this case, we see an effect of localization that is clearly different from the excitonic mode. And this effect of localization is again due to the interaction, but in this case, it's a repulsive interaction. It's not an attractive interaction, which means that the localization of the two-particle wave function is always a sign of interaction, is always a consequence of the interaction, independently of its sign. Now, again, we can ask a question, can we measure this? And so far, this is just a theoretical prediction. And we hope, again, that we can motivate experimental friends to try to measure this new collective mode. Where can we find this? Where we can hope to find this kind of excitation? Well, for example, in doped semiconductors or interfaces, where we can think that there is some electron gas. In materials that are photodoped, so in time-resolved spectroscopy, where you excite electrons from valence to conduction. And this is important for different applications, for example, for the exciton mode transitions, for those of you that are experts, because here we are showing that we have to go beyond this Thomas Fermi representation of macroscopic screening that I've just mentioned, that is typically used to describe the exciton mode transition. And these effects are supposed to be found in materials that have low density, very low density, lower than the case of sodium. So this can be difficult to realize. So the other possibility is to look at 2D electron gases. And in 2D electron gases, we have just studied in a collaboration with Jakob and Silvana from Jena, the same kind of question. And also in the 2D electron gas, besides the common plasmon that has a square root dispersion, there is again a collective mode that has the same origin, excitonic origin. So also in the 2D electron gas, this new fingerprint should be visible. And we think that all this is very interesting. I didn't explain so much the origin of this new collective mode because this is a bit technical. But since we are at the LPS, please let me at least mention the connection with Friedel and Friedel oscillations, because here I'm representing the screen Coulomb interaction in real space, and you see that there are all these oscillations. These oscillations are related to the Friedel oscillations. So there is a one-to-one correspondence. It's important to say that the change of sign of the static screening doesn't affect these oscillations. And it's in order to take it to be able to describe this new collective excitation, we have to go beyond the standard approximations that we use in this Bethe-Salpeter equation. We have to take into account the fact that electrons are really quantum in nature. So we have to take into account the quantum nature of the electron interaction and the screening. This is quite technical, so I will just flash about this. Is the fact that, again, the screening is perfect only at long distances, not at short distances. And at short distances, the interaction can be actually very strong. So this can be and should be taken into account. There is also something related to exotic excitations like ghost excitons and to the physics of exceptional points that I will skip. If you are interested, again, this is the reference. And I think that I am over with time, right? So I think I will stop here unless you really want to know more about applications in materials and connections about spectroscopies. But for this, you can ask questions and I can show some other works that I've been done in collaboration with people in the room. So again, if you are interested, you can also ask your colleagues in the room, maybe not now, but in other occasions. And again, I invite you to talk with them because it's really a lot of fun that we have enjoyed together. So with this, I hope that I have at least give you a glimpse of the fact that correlation sometimes can be understood in terms of coupling of different excitations. I have talked about these collective excitations that are plasmons and excitons. I have revised classical topics like the homogeneous electron gas or excitons in insulators, but I've shown you that we can find surprises even in these classical topics. I've chosen then for pedagogical reasons, the variety of correlation effects in materials is huge. So again, it's just a matter of talking with your neighbor to have other surprises and fun. And the message from the strategic point of view is the fact that in order to understand better the effect of electronic correlations, a convenient strategy is to team up together and to exploit the fact that we are really very much complementary. And there is a lot of complementarity between different spectroscopies that can be performed at labs like the LPS, at synchrotrons, and in different places. And as a theoretician, I think that theory is, of course, useful when it's able to reproduce and to interpret the experiments. But it's also important, as an important role to play, when theory is able to make experimentalists work better together. And again, there is a lot of fun in doing all this. There is something that I have not discussed at all, and it's the fact that there is always a lot of work to do to bridge theory and experiment, because very often what we calculate and what is measured is not the same. So there is a lot of work that has to be done there, and a lot of surprises also there. And as outlook, all this was related to excitations starting from the ground state. Nowadays, it's possible also to study the electron dynamics using time-resolved spectroscopy. And we are trying now to export all these concepts to try to understand and to support pump-up experiments that are done in different places, and in particular at free electron lasers, like in Hamburg or in Trieste or in different places in the world. And again, I think that experiments help improving theory, providing new challenges and benchmarks. And theory helps improving the experiments for the same reason, providing challenges and experiments. So it's, again, a claim that we should try to work together as much as possible. And with this, I would like to thank you for your patience and for having being here all this time without asking questions, but now it's the time for you to ask questions if you are interested. And thank you very much again.
Any question?
Thank you. So I'm very surprised about your ghost plasmons and excitons and how they are related to exceptional point. Can you tell a little bit more?
So you are actually interested in the part that I have not discussed, right? If
Exactly.
I understand well. No, it's good because this gives me the occasion to talk a bit also about this. So it's possible to demonstrate, and this is not our work, but it's the work of these two people, Takayanagi and Liparini, that in the regime of negative screening, so in this regime where the the electric function is changing sign, now this is a bit technical, but the irreducible polarizability that is related to the full polarizability by this Dyson equation should have imaginary poles. Normally, this P is related to the electric constant, while chi is related to the inverse electric constant. This again a bit technical, but just to give the names. So it's possible to demonstrate that there is a one-to-one correspondence between negative screening and imaginary poles. And these imaginary poles have been called by them ghost plasmons. Now, in the work of Takada, who is the first person that it's the other directions. Yeah, it's the first person that has discussed these new collective modes here. He suggests to name them actually ghost excitons because he had the claim that this excitation has an excitonic origin, and it's indeed the case. So we can call them ghost modes that can be called plasmons or excitons, depending on how you call them. Now, the point is that these are poles that are going from being real to being along the imaginary axis. And at the point where these poles are zero, this is an exceptional point because you have a point that has the same energy, and you can demonstrate that this is an exceptional point. Now, all this is fancy from the theoretical point of view, but unfortunately cannot be measured because this P is not measurable. The quantity that can be measured is chi. So the interest, I would say, here is just fundamental, but the real interest is the fact that we can also look at the 2D gas. You should be able to measure this excitation. It is a pole of something that can be measured because it's in the inverse electric function. There is a connection between the two, these ghost modes and this collective excitation. They are both related to the negative screening. This can be measured, and this can make the life of theoreticians funny, because we can say that there are these imaginary modes, but cannot be measured. So I hope I'm not disappointing you.
Usually, when you have an exceptional point, from what I know, it's linked to some non-ematicity of some Hamiltonian. So what's the difference between the real excitation? Why is the non-ematicity here?
The Hamiltonian is non-Hermitian. I have to go back. Okay, in the wrong direction. The simple Hamiltonian I show you is actually non-Hermitian. This one. This Hamiltonian is non-Hermitian. So it is allowed to have imaginary solutions. And the exceptional point is just one particular case where there is one pole that has zero energy in this case.
Yeah. Thank you.
Thank you. There are another question. You have a question.
I was wondering about the helium calculations. Do you expect a difference between solid and liquid? Because at so high energy, maybe solid and liquid are pretty much alike.
Yes, indeed. Yeah, indeed. There have been measurements in liquid helium by inelastic ray scattering, and so you can put them in this graph of the excitation energy as a function of pressure, and they would stay in the same graph. Sorry, it's here. Okay. But this effect of the anisotropy clearly is not there for liquids because it has to do with Bragg reflections.
Okay, so I think we are going to thank Matteo again.
Thank you very much.